Nomine Patris et Filii et Spiritus Sancti. Amen. Veni Sancte Spiritus, repleturum corde fidelium, et tui moris in eis signum accende. Emitit Spiritum tuum et creabuntur, et renovabis faciam terrae. Oremus, Deus, qui corde fidelium Sancti Spiritus illustratione docuisti, da nobis in eodem Spiritu recta sapere, et Deus semper consolatione gaudere per Christum Dominum nostrum. Ave Maria, gratia plena Dominus tecum, benedicta tu in mulieribus, et benedictus fructus ventris tui, Iesus. Santa Maria, Mater Dei, ora pro nobis peccatoribus, nunc et in hora mortis nostrae. Amen. Sit sapientiae, ora pro nobis. Sancte Roberte, ora pro nobis. Sancti Philippe et Jacobe, orate pro nobis. In nomine Patris et Filii et Spiritus Sancti. Amen. In this video, we'll examine the similarities and differences between the geometric mean and the arithmetic mean. Okay, the arithmetic mean is what we sometimes call the average. This is what you're used to calculating when you find an average for some numbers. And the geometric mean is also a kind of average, although we'll see the differences in a moment. And some of the ways that the geometric mean it gets used or comes up in geometry, and it's also connected to the idea of proportions, which we've been studying recently. So let's think about the arithmetic mean first, since that's what we're familiar with. If I have a group of numbers like 3, 7, 12, 32, and 10, and I want to find the average or the mean of those numbers, the arithmetic mean at least, then what I'm going to do is I'm going to add all of those numbers up, take the sum of all of them, and then divide it by the number of numbers that I have, okay, or the number of items that I have that I'm averaging. So there are 5 numbers being added here, so we divide that by 5, and that will give us what we call the arithmetic mean, or our average. So in this case, it's 20, 32, 64 divided by 5, which is about, 12.8 or so. Okay, and what this number represents is a way to get to the total, sort of an average number that if I add it to itself again and again, or in this case 5 times, if I take 12.8 and I add it to 12.8 5 times, so 12.8 plus 12.8 plus 12.8 plus 12.8 plus 12.8, that I'll get the same sum as I did from adding all of these other numbers up. So it's sort of like the average amount of the average number that we're adding each time in order to reach this total. And so it's the mean is a kind of a rate. It's almost like a speed at which we get to some number. And the geometric mean is also a rate, but instead of adding, we're going to be multiplying. So this isn't, this is a mean based on a sum. Okay, that's basic arithmetic. This is a mean based on a product, okay, or a result of a multiplication. So the geometric mean, we would do this instead. We would say 2 times 4 times 2 times 3 times 4/3, and we would find what that product is. So the geometric mean for these numbers is going to be based on the product. And since we're multiplying, instead of dividing here, what we're going to actually end up doing to find the geometric mean is take the root. Okay, so the geometric mean is connected again to this idea of the square root or of some root of some power. Okay, so to find the geometric mean of this group of numbers, there are 6 numbers here. That means I'm going to need to take the 6th root of whatever this product is. So instead of adding these, we're going to multiply them. So if I multiply 2 times 4 times 2 times 3 times 4/3 times 1, the product ends up being 64. Okay, we didn't add them, we multiplied them to get this sum. And if I take now instead of dividing by 6, because there are 6 terms, I'm going to take the 6th root of 64. So in other words, what number multiplied by itself 6 times would give me 64? And we won't worry about how you are supposed to know this, but I know that the sixth root of 64 is 2. So the geometric mean of this group of numbers is 2. And in general, you'll notice this is relatively small. In general, the geometric mean is going to be less than the arithmetic mean of the same group of numbers. So if I took the arithmetic mean of the same group of numbers, if I added all of these and found the arithmetic mean, so these add to 13 1/3, and then I divided by 6, you get 2 2/9. You'll notice that the arithmetic mean is larger than the geometric mean. Okay, and that is always going to be true. The geometric mean of the same group of numbers will always be smaller than the arithmetic mean. And it's because we're doing this root thing instead of dividing, which reduces the size of the number more quickly. So that's what the geometric mean is, and that's its sort of relation to the arithmetic mean. The arithmetic mean is it's an average number that if I added would get me to some total a certain number of times. The geometric mean is the average number that if I multiplied it would get me to some total. So if I did 2 in this case and I multiplied it by itself 6 times, if I took 6 2's and multiplied them together, I would get this same result as I did from multiplying all of these terms together, 64 and 64. Okay, so it's like saying on average, if I multiplied by 2 or if I multiply at this rate, I will get the same result as if I multiplied these all straight across. Okay, so that's the similarity, but it's also obviously quite different. Now, we won't be using any of the roots other than square root in this class, but you can. Okay, in general, the geometric mean, depending on how many terms you have, you're going to have a different value for the index of the root that you're taking. But we're just going to be working with 2 terms at a time, so we're only going to need the square root. So an example of that would be like if I were asked to find the geometric mean between, say, just whatever 2 numbers you might want to choose, let's say 5 and 11. Okay, if I were finding the arithmetic mean, I would add these and then divide by 2. So the arithmetic mean would be 5 plus 11 divided by 2 would be 16 divided by 2, which would give me 8. So I should expect the geometric mean to be less than that. The geometric mean I find by multiplying the 2, so 5 times 11, and then taking the root that corresponds to the number of terms I have. Here I have 2 terms, so I'm just going to take the square root of this product. So I get 55 for the product, and the square root of 55 is my geometric mean. Okay, again, I can try to simplify this, but in fact, in this case, there are no perfect squares that I can pull out of and factor out of 55. So I'm just going to leave it like this. Okay, and square root of 55, if you put it in your calculator, you'll find is about 7.42 approximately, which is again less than the arithmetic mean for the same group of numbers. Okay, so that's really just all algebra and arithmetic though. What does this actually have to do with geometry? Well, if you remember in proportions, when we set up a proportion, we have names for these terms in the proportion. And the terms at the numerator of the first fraction and the denominator of the second are called the extremes. And the middle terms are called the means. And if I were to cross multiply this proportion, I would be multiplying these 2 means. I'd be multiplying these together and I'd be getting some product. Well, that's pretty much what we're doing when we're finding the geometric mean. We're going to multiply 2 terms and then take the square root of it to maybe solve for something. So where this comes up is in situations like are described for the first theorem of this chapter, which is theorem 8.1. If the altitude is drawn to the hypotenuse of a right triangle, then the 2 triangles formed are similar to the original triangle, and to each other. That's a lot of words. Let's see what it means visually. It means that if I have a right triangle, okay, so say this large triangle here, let's call it ABC, and I draw an altitude to the hypotenuse of ABC. So altitude means this is going to be a right angle here. That this altitude is going to divide this triangle into three triangles which are now similar. I have the original triangle, this right triangle on this side of the altitude, and this right triangle on the left side of this altitude. So I have now three similar triangles which are created simply by drawing in that altitude. That's what the theorem is saying. How do I know that this is the case, that these are all similar? Well, because if I have a right angle in this triangle and a right angle in this triangle and a right angle in this triangle, and then I look at another angle in each pair of triangles. So if I say the large triangle contains angle A and this triangle on the left side of the altitude contains angle A, well then I have a right angle and a shared angle. So I have two pairs of congruent angles. That means by angle-angle similarity that those two triangles are congruent, or excuse me, similar, not congruent. And then the same thing here, if I have a shared angle at C, a right angle, and a shared angle, then those two triangles are similar to each other. The large triangle is similar to this triangle, BDC. And if both of those are similar to the large triangle, then that means that they're also going to be similar to each other. Okay, so all three triangles are similar to one another in this situation. And it turns out that there are many relationships here between these three triangles which are going to use the geometric mean. So since theorem 8.1 tells me that ABC, this large triangle, is similar to ACN, which is similar to CBN, these three triangles are all similar, I can use proportions. I can set up proportions based on that similarity. And what corollary 1 is going to tell me to this theorem is that this altitude length is the geometric mean between the segments of the hypotenuse. So this altitude divides the hypotenuse into two segments. And if I set up a proportion between this segment and the altitude in this segment, then that will be the geometric mean between the two. So let's see how this works in terms of how we're used to doing this. I know that this triangle is similar to this one, and so I can create a proportion using the corresponding sides that are in proportion. So 5 to x on triangle ADB is the same ratio as x to 7. Okay, or we were saying here AD compared to BD is equivalent to BD compared to DC. And when I plug the numbers in, I get this. 5 over x is equal to x over 7. And if I were going to cross multiply this and solve for x, okay, to find the length of this, I would take 5 times 7, which is what we do when we're finding the geometric mean. We multiply two numbers, is equal to x times x, which is x squared. And then to find x, I need to take the square root. So what I'm really doing here is I'm saying x is the geometric mean of these two numbers, 5 and 7. So x is the square root of 35, okay, which will not simplify in this case. And so this is what the corollary is saying, is that this will always be the case when I have a right triangle with an altitude going to the hypotenuse and dividing it into three similar triangles, that the length of that altitude is always going to be whatever the geometric mean is between these two segment lengths of the hypotenuse. Okay, and then there's a second corollary that also uses the geometric mean. Okay, so I went ahead and rewrote these corollaries out so that we can see them in writing a little bit more easily. We already discussed corollary 1. When the altitude is drawn to the hypotenuse of a right triangle, its length is the geometric mean between the segments of the hypotenuse. So again, for illustration, what that is saying is that the length of this altitude, z in this case, is the geometric mean between these segments that it creates on the hypotenuse. So I can find z by taking the geometric mean of these two numbers. So z is 5 times 7, and the geometric mean is the square root of 5 times 7. So root 35. Corollary 2 says that when the altitude is drawn to the hypotenuse of a right triangle, each leg of the original right triangle, so x and y here, is the geometric mean between the hypotenuse and the segment of the hypotenuse which is adjacent to that leg. So x is the geometric mean between the hypotenuse of the whole triangle, which is 12, 5 plus 7 here, and the segment that is adjacent to that leg. So if I'm looking at x, x is the geometric mean between 12 and 5. 5 is the adjacent piece here to x. So x is going to be the geometric mean of 12 times 5. Of 12 and 5, excuse me. So square root of 60, which is root 4 times root 15. And root 4 is 2. So it's 2 root 15. Okay, and then y, this same corollary is also going to tell us the same thing for y. Y is the geometric mean between 12, the hypotenuse, and the segment that is adjacent to y, which in this case is 7. So y we can find by using the geometric mean between 12 and 7. 12 is 4 times 3. Root 4 is again 2, so I get 2 times root 3 root 7, which is root 21. Okay, so in this situation, we don't even have to necessarily set up the proportions. We could get these same values by doing what we've been doing before in chapter 7 and setting up proportions between the corresponding sides of these similar triangles that are created. But since in these particular cases, these values happen to be geometric means, we can just use what we know about the geometric mean to calculate them in a sort of a shortcut and a quicker manner. All right, so that's a lot of words. Let's look at some example problems of how we can use this in practice. Here I have a right triangle. I only know the length of the hypotenuse of the right triangle and one of his legs, and I don't know any of these other values. But using theorem 8.1 and the two corollaries, we can actually solve for all four of these relatively easily. So corollary 2 said that the side length is the geometric mean between the hypotenuse and the segment of the hypotenuse that's adjacent to that leg. So 6 here is the geometric mean between 18 and W. And so we can sort of, this one is, we're going to kind of work this in reverse. We actually need to do, instead of finding the geometric mean, we know the geometric mean from this side, and we're going to have to solve for one of the other unknown pieces that it came from. So if we square both sides here, we get 36 is 18 times W. And when we divide by 18, we'll find that W is equal to 2. And if W is 2 and this whole length of the hypotenuse is 18, then that means 18 minus 2, x is going to be 16 here. And y is the geometric mean between these two segments. So y is the square root of 2 times 16, or root 32, or if I just think of this, root 16 is 4, so this is 4, y is 4 root 2. And then this last leg, well, this is going to be, like in this one was 6, this is going to be the geometric mean between 18 and x, between the hypotenuse and this segment that's adjacent to it. So z is the geometric mean between 18 and x, which is 16. We already found x to be 16. Again, root 16 is 4. Root 18 can be broken into 9 times 2. So I get 4 times 3 times 2. So this is 12. Z is 12 root 2. Okay, and so using that theorem and the corollaries which are attached to it, we were able to find all 4 of these unknown pieces given only 2 parts of this triangle. Here's another situation. We have another right triangle. This time we know one of the segment lengths here that the altitude divides. We know root 2, and then we don't know the other piece. And we know one of the legs. So again, I'm going to start with the pieces that I know. I know that this leg of length 2 here is the geometric mean between the whole hypotenuse. Let's call this Q, I suppose, and this segment that's adjacent to it. So this is 2 is the geometric mean between Q and root 2. Okay, so again, to free this from underneath the radical, we're going to need to square both sides. So 4 is Q root 2. Okay, the squaring here just eliminates this top radical. And then I solve for Q by dividing by root 2. So Q is 4 over root 2. And again, this is just a reminder, when you have a root in the denominator, we don't like that. We want to simplify by rationalizing the denominator. So here I would multiply by root 2 over root 2 so that I square this root 2 and I eliminate the radical in the denominator here. 3 goes into 24 8 times. So I have 8 root 2 over 2. Root 2 times root 2 is 2. Okay, when I square I get 2. So this, for example, this expression would simplify to 4 root 2. We have a similar thing here. We have a root 2 in the denominator. We're going to want to rationalize that. So we multiply by root 2 over root 2. And so we get 4 root 2 over root 2 times root 2, which is 2. That reduces, and so Q here is 2 root 2. So we have 2 root 2 and root 2. Are these two, excuse me, yes, 2 root 2 is the whole side length. So what would x be then if I know that the whole length of this hypotenuse is 2 root 2? Well, 2 root 2 is equal to x plus root 2. So if I subtract a root 2, then what do I have left? Well, 2 root 2's minus 1 root 2 leaves us with 1. So x is also root 2, just like this segment was. So this is a situation where this altitude is coming to the midpoint of the hypotenuse, in fact. So x is root 2. We could now solve for z. Z is the geometric mean between this segment and this segment. So it's the square root of this times this. Root 2 times root 2 is 2. So z is the square root of 2 also. So this is also square root of 2. So we have root 2, root 2, root 2, 2 on this side. And I'll let you guess what this is going to end up being, but we'll solve for it algebraically. So this side length is the geometric mean between this piece, root 2, and the total length of the hypotenuse. So again, y is the square root of root 2 times 2 root 2. Root 2 times root 2 is 2. Times 2 is 4. So this is the same thing as root 4, which is just 2. And so just like this side was 2, y here is also going to end up being 2. Okay, so these are the examples of the types of things we can do with the geometric mean. And in the next lesson, we're going to see how we can actually use this theorem and these corollaries to prove the Pythagorean theorem. Okay, that the Pythagorean theorem is actually, it works, There are many ways to prove the Pythagorean theorem, but this is, in fact, going to be one of them, and the one that we will use.